one for this session. It's Mr. Yamakami from Yukui. And the title is Straight Construction of Non-Interactive Quantum Bit Commitment Schemes for Indistinguishable Quantum State Ensembles.
Well, thank you very much for the nice introduction. So my talk is all about quantum bit commitment, QBC. And in this particular talk, I'm presenting or proposing is two schemes for the quantum bit commitment, QBC. And I'm going to give security conditions. Two security conditions have to be met for the scheme to be guaranteed to be secure. So this is all about the quantum information theory. So some of you may not be really familiar with the concept. So I just give you a very brief introduction to the quantum information theory. So in the quantum information theory, the unit of the quantum information is called the quantum bit or qubit. That is compared to the classical bit 0 and 1. That is actually written here. So conventionally, we will use the notation like this one, Ket notation. So this is the Dirac's notation. And quantum bit is the manifestation of the small, tiny particle that's spinning around. And usually, people think that if the spin head looking upward, that corresponds to the classical bit 0, and the spin head look downward, and that is corresponding to the classical bit 1. But there are different kinds of the representation. For example, if you look at this in picture here, the electrons in a circle around the nucleus, and then they stay in a different orbits, and then one orbit corresponds to 1, and the another one corresponds to 0. So that the one single electron could possibly stay in two different orbits. So that's the linear combination of 0 and 1. That is quantum information, quantum bit. To get the information out of this quantum state, then we have to make an observation or measurement. The measurement and unintentionally, plus this nice quantum state into classical state. So we only get either 0 or 1 in the classical sense. It's nothing else, with some probability. And the very nice thing about the quantum states are happening if you have the particle more than 1. For example, if you have two particles, they can be correlated. So the correlation is called entanglement. So for example, if you have some correlated particle, two particles like this one, Bob has one particle and Alice has another. And if Bob look at the one particle and find out that this is 0, then the Alice automatically get 1 without even communicating with the Bob. So that's the kind of a transmission of the information without sending it. So this is actually the basis for the lots of very nice protocols, including BB84, it's a secure communication key distribution. The quantum computation, on the other hand, is something like the modification of the quantum state. Usually, well, in this particular slide, I use the quantum circuit. The circuit is composed of the quantum gates. The quantum gate manipulate, well, technically speaking, it just rotates the particle. That's it. And in the communication, the quantum information theory is used in the communication situation. In a classical sense, then Alice and Bob have a classical communication channel. Then they send classical bits back and forth, right? In a quantum situation, they have a quantum channel instead of the classical channel, so they can actually transmit in a quantum state. It's a very simple model. You actually use the fiber optical cable so that you can actually send the photon. The photon is a particle. That represents a quantum bit. In general, the classical information and the quantum information are very, very different. So that we actually exploit that difference to enhance the better communication protocols. I'm not really going to the teleportation things. That you just use the entanglement to actually send a message without sending it. That's a little bit spooky, but it's very simple, mathematically speaking. So now we go back to the business. So the quantum bit information, quantum bit commitment, QBC. The QBC is based on the BC, bit commitment. Bit commitment is one of the building blocks. And if you want to build the very large scale quantum system, cryptographic system, then you have to actually make it according to just piling up the small blocks. That is called the primitives. And in this particular talk, I'm talk about the bit commitment. That is one of the cryptographic primitive. And this particular primitive has two phases. First one is the committing phase. So the Alice and Bob are communicating with each other. Then Alice first commit to a bit, and then eventually the message is sent to Bob, and Bob keeps the message. And in the end, in the opening phase, Alice actually reveals what the committed bit is, and then Bob make her checking whether that is actually correct or not. So in the slides, that explains what exactly I said. So the first Alice commit to a bit, and then she actually encodes it, encrypts it, and then send a message. Part of the message called the reduced quantum state. So that you actually prepare 10 qubits, and then you just send in only 3 of them, kind of thing. So the Bob in the opening phase, Alice reveals her committed bit, and then Bob actually check whether it is correct or not using some reduced information he already got in the first phase. So we have to guarantee that this protocol is secure in terms of the hiding condition and binding condition. The hiding condition is explained in the following way. So hiding condition ensures that the Bob in the first phase, then Alice commit to a bit, and then send some encrypted message to Bob, and Bob does not know what was sent, right? So if he knows what it is, and he actually take advantage of knowing it and make her some kind of produce some cheating strategy to get some benefit out of it. But anyway, so the hiding condition said that Bob has no knowledge of what he got. Now the hiding condition. The hiding condition. So there are two different kinds. In particular, in this particular talk, and so I'm going to explain about the computational hiding condition and the perfect hiding condition. The computational hiding guarantees that for any given polynomial, no matter how Bob run this quantum computation in the polynomial time, but he knows the probability of he actually getting the right answer, the committed bit A, with probability half plus 1 of a polynomial. That's really, really close to a half, so that he only guess what it is. In a perfect hiding situation, that he the probability of Bob getting the right answer is 0. So that means perfect. So all the information that Alice hide the information perfectly. The binding condition, on the other hand, is about the Alice. So now, Alice, from Alice's point of view, she actually committed to say 0, and then eventually she changed her mind, and she actually tried to cheat Bob, saying that, well, I committed 1, right? The Bob tried to avoid that kind of situation, so that no matter what Alice tried to cheat him is that he has ability to detect it, right? So that's about the binding condition. So the binding condition says Alice cannot change her mind to cheat Bob during the whole entire process. And for example, the Alice wants to cheat Bob, then she actually prepared some encoding that could be 0, could be 1, maybe both ways. So that she actually changed her mind later on, right? And then she actually used some trick during that, between the process, and then she actually said, the completely opposite message to Bob in the reviewing process. And then, but the probability of getting the, here are. So I'm going to talk about two different kinds of the binding condition, computational binding and statistical binding. The computational binding says that no matter how hard Alice tried to cheat Bob, but Bob, the probability of successful, probability of success for Alice's part is just a half plus very small function, the negligible function. So it's very close to a half. So she has no advantage in cheating him. In a statistical case, well, Alice can possibly use, unconditionally complex, computation, the time unbounded computation, the cheating strategy. But still, she can't cheat Bob. So that's the statistical binding condition. It is known many years ago that if you try to, build, this QBC, the quantum bit commitment scheme, with guaranteed security, well, we can't do it. So this is actually kind of a limitation of the QBC. So that means we can't build the scheme that is both statistically hiding and statistically binding. So that if you want to try to build a scheme, you have to weaken one of them, at least. So now I'm going to propose two schemes. But before that, I have to explain a little bit about the quantum state. Now, I prepared a symmetric group of degree n, and then so I'll define it in a particular subset of this symmetric group that satisfies two conditions. Pi, and this is the permutation, and the pi of I is not going to I for any I, but if you actually try pi twice, then you just get the identity permutation. So something like this one. And 1 goes to 4 and 4 goes to 1. So you apply pi twice to 1, then you actually get the 1 again. But then 1 is not mapped to 1, right? But we have tons of such permutations, so that the K0 is not so small. So you have plenty of room to choose good pi. So now, depending on this particular pi, we create a particular kind of quantum state, well, actually the ensemble of the quantum state. That is this big phi, phi sub b, and b is 0 or 1. And the structure of this, the big phi is something like that. And the first register, and we have the first register and the second register. And the first register contains all possible permutations, and the second register contains this particular quantum state, depending on this sigma, and the b. The b is actually the choice of the committed bit, like either 0 or 1. So that's actually here, right? And now we consider a reduced state. That is actually the rho sub 0 and the rho sub 1. And that is actually the traced out form of the quantum state. That becomes the reduced state. And which means that now we have the first register, the n, well, technically speaking, n log n. N log n many quantum particles here, and another n log n quantum particle in the second register, and then we just simply cut them half and then just consider only half part. So that is the reduced state. We are not doing anything, just looking at just one register. That's it. So, but notationally, mathematically speaking, we actually get this particular state. Well, this is just a notational thing, so don't worry. So now, we prepared row 0 and row 1, two different quantum states. Those ensembles has a very nice property. What kind of property is it? And that's the distinguishability property. So supposing someone actually pick one of them and then send it to you, and then you actually determine whether the given quantum state is either row 0 or row 1. So you have to make a decision. But it turned out that it seemed to be really, really hard. Because as I said, if you want to see what it is inside the quantum particle, then the quantum particle collapses to the classical state with some probability. So there is there is no chance you actually really find either row 0 or row 1. If you try it 1,000 or 1,000,000 times. But in the quantum theory, it said that cloning is really hard. Technically speaking, if you don't know what it is, you can't make a copy. So, so if you know pi, then you can create row sub 0, and you can actually convert from row 0 to row 1. It's a very, very simple operation. It's that's written here, phase encoding, and just to control pi and the Hadamard gate kind of thing. It's very simple. And if you know pi, then you can actually distinguish between row 0 and row 1. But if you don't know what pi is, it's really hard. So this is actually this property is called the trapdoor property. And so this is actually the actual statement. Really hard to distinguish those quantum states. And if you possibly distinguish them, and the result is something like you can actually classically solve the open problem, NP problem, the graph automorphism problem, in polynomial time in a classical sense, right? Okay, so this is just relevant background, and I just kind of didn't skip it. And to describe precisely what the assumption that I'm going to use, and I introduce the actual problem, so-called KQSCD. Well, it's a acronym of the quantum state computational distinction problem. So that you are given this two quantum states in row 0 and row 1, and k many, so that you actually get a whole bunch of the same copies. Now you have to somebody actually sends you either one of them, right, and k many copy of the one of them, and then you have to judge whether the given quantum state is either quantum 0. Then in that case you actually say yes, but otherwise you say no, right? So this is the problem. And this problem, well, I just introduced some kind of a terminology. Quantum algorithm or quantum computer solve this particular problem with advantage P of n with respect to pi, the given fixed pi. That means that the distinction between the row 0 and row 1 is exactly P. And when I said that an average advantage gamma means that expectation or average value of this advantage is exactly gamma, provided that the pi is actually chosen uniformly at random. Now it's the final phase. I'm going to present the second scheme first. Sorry. Okay, so I'm prepared three operations, and the P1 start and P2 and then the PSPA. And the P1 start and actually to modify and generate phi sub 0 from identity permutation. So this is actually very simple. And P2 transforms the B of the, if you just look at the subscript here, B to B minus 1, so that the phi 0 goes to phi 1, then phi 1 goes to phi 0. So it's just switching the subscript. And the last one is a little bit tricky one. So that if you're given in the quantum state, reduced quantum state chi, then you can actually partition it into the 0 part and the 1 part. And those are actually perpendicular in some sense. So now, this is the actual protocol. So in the committing phase, Alice start with all zeros. Those green areas registers are actually belonging to Alice, and this dark one belongs to Bob. Okay, so she start with all 0, and then choose the secret key pi in open 2. So here, and then she prepare the identity permutation in open 1 and com. So the open 1 here and the com, the communication register in the sense. And she actually didn't generate an all equally probable quantum states sigma, and then create phi sub 0 in a hole here. Okay, so now she's choose a committed bit 0, 1, and that's stored in this H bit. Now she has to encode, change A and phi sub 0 into A and phi sub A. So then she actually changed this subscript 0 to A, depending on the value of A, right? And now she sent this H com to Bob. So this is the reduced state and sent to Bob. Now, so that's the end of the committing phase. Now we are actually moving on to the opening phase. So suppose that Bob received the chi in the earlier phase, and then she sends a bit and open. So she actually reading her committed bits and some additional information to Bob. So Bob received the whole entire thing except that small tiny green area. Okay, he start with check the content of H bit and H open 2, so that here and here. And if he finds A and pi in some superposition, it's just a mixture of those A and pi. If pi is not in the right form, then he knows that Alice tried to cheat, right? So then he actually said, "Well, you cheated." Otherwise, and Bob applied PSBA, that's the partitioning algorithm, and then he actually gets something here. Now he continues doing. So he actually make a measurement. So he observed the content of his own register, and then if this one is not matched with there's something in this H bit, then he knows that Alice cheated. Otherwise, if A is 1, then Bob changed phi sub 1 to phi sub 0, and then applied P1 star inverse, because quantum computation is reversible, so you can actually go in this way and that way, right? So, and take a look at the inside of this H bit, so the observation, and then if that, he measures open 1 and the com using this 0 and the identity the permutation. If he finds 0 and the identity permutation, he knows that A is a correct committed bit. Otherwise, he said that, well, you cheated. So that's the whole entire the protocol. And this protocol guarantees the computational hiding and the statistical binding. As I said, we can't achieve both statistical hiding and statistical binding, but this protocol achieves the computational hiding and the statistical binding if KQSD is distinction between QZ and row 0 and row 1 is really hard for quantum computers in a polynomial time. And the first scheme, I'm going to go into detail for the first scheme, but the first scheme is a simple modification of the second scheme, or the other way around. But the first scheme achieved perfect hiding and computational binding. If you just make a comparison between the first one and the second one, the difference between them is just the strength of the hiding and binding conditions. Now, then I just quickly mention about it in the future challenges. So I proposed two schemes, but those two schemes are based on the permutation. The permutation is represented by the n log n bits or qubits. So that's too much. So it's better to have much more concise and also smaller system somehow. And another one is the finding application of the quantum state ensemble, then row 0 and row 1. So far I know the two applications, the quantum public key crypto system and this work in quantum bit commitment, maybe something else. And also find some useful properties or features of this particular ensemble, because then that's the source of this two schemes. Well, thank you very much for listening, and now I'm really happy to take your questions.
Any question? No.
I think that everybody's...
Let me expose my ignorance.
No, that's okay. Just ask me a question.
I don't know anything about those building blocks and what they are for. Is it for, you want a remote computer to make a computation without knowing the data it is working on? This is the basic...
So you're talking about the bit commitment or the more general things?
If I understood right, the bit commitment is just one building block in a set of building blocks.
That's right.
And those building blocks are for what?
For example, I did not really kind of explain everything, but there are several applications like multi-party communications, secure communications, and zero knowledge proof system thing.
Yes, and is it related to the test of? I mean, if you want a computer to make a computation on some data, but without knowing the data it is working on, is it related to?
Yeah, so if you want to build some kind of big crypto system, you're just plugging this, the communication part in somewhere, because then we know that the security is guaranteed in that block, right? So you just put all the blocks and then just make a big system. Okay.
Maybe I can answer this. Bit commitment is one building block, but you also mentioned oblivious transfer. And if I remember correctly, if you can do oblivious transfer, I think you can do any two-party cryptographic model.
The cryptographic model is just communication?
No, it could be much more. It could be signature, it could be many things.
Yeah, that is one of
It's
them.
three-party, I'm not sure, but you can do many things.
Okay, so let's thank the speaker again.
Thank you very much for listening. Yeah, it's lots of animations, and I like that.